Hey everybody, Dr. A here, and in this video we're going to be providing some more detailed background information on the hydraulic conductivity of soils. So let's go ahead and get started. It turns out that the hydraulic conductivity of soils, which we sometimes call coefficient of permeability, depends on several things. It depends on the fluid viscosity of the fluid that's flowing through the soil or the porous media, which in most cases we're dealing with water. It depends on the pore sizes of the soil grains. It also depends on the grain sizes or the grain size distribution of the soil particles themselves. It depends on the void ratio of the soil, the particle roughness of the soil particles, the temperature, and the degree of saturation. So you can see a lot of things will affect what the value of a hydraulic conductivity of a particular soil is. Now, it also varies widely for different soils, but I would say what is the most influential attributes for hydraulic conductivity really are pore size, grain size, and void ratio. That seems to have the greatest impact. So in general, let's write this down. In general, finer particle soils have a lower hydraulic conductivity. Again, we call that K. So for example, if we were to kind of draw this out in like a little flow chart, okay, lower hydraulic conductivities would be like your clays, okay? And then you would get to your silts, and then you would get to your sands, and then you would get to your gravels. And what happens is hydraulic conductivity will tend to increase as you go from these small clay particles to small but slightly larger silt particles to the larger sand particles to the very large gravels and so on. Okay, so this is in general. All right, now also it is conventional. I'll write this down. It is conventional to express hydraulic conductivity, which again we call K, at 20 degrees Celsius, okay? And so what we can do is if you have a temperature of the water or of the system that is different than 20 degrees Celsius, you can apply a temperature adjustment factor like so. You can say the equivalent hydraulic conductivity at 20 degrees Celsius will be equal to the viscosity of your water at whatever temperature in Celsius that you have divided by the viscosity of the water at 20 degrees Celsius, and you multiply that by the hydraulic conductivity at that temperature that you are dealing with. So again, this little subscript right here, capital T degrees Celsius, this value refers to the hydraulic conductivity at some other temperature T that may be bigger or greater, or bigger or less than 20 degrees Celsius. And then these mu values are viscosities of the water that's flowing through the soil. The numerator is the viscosity of the water at the temperature that you're dealing with, and then the denominator is the viscosity of the soil at 20 degrees Celsius. Okay, so again, we'll say mu is water viscosity in general, and it's the water viscosity at T degrees or 20 degrees when you're looking at the denominator there. Now, another thing that you can define related to all of this is what's called the absolute or intrinsic permeability. So let's write this down. We're going to say the absolute, let's see if I can spell things right, absolute or intrinsic permeability of the soil is sometimes expressed as capital K, and you can put a bar or a prime over it, and that's going to be viscosity times the little k value over the unit weight of water. And so there's some applications in other subtopics of geotechnical engineering that use the absolute or intrinsic permeability of the soil instead of the regular permeability, little k. All right, so then the next question becomes, how do we get these values? How do you determine permeability K? Well, there's several ways of doing it, okay? So let's list those out, and then we're gonna have other videos that go into those different methods in more detail, okay? So I'm gonna say determining hydraulic conductivity K. All right, so we can do it in the lab, okay? In the lab, we have two very common tests that we can perform in the lab, okay? One of them is called the falling head permeability test, okay? The second is called the constant head permeability test, all right? And these are both performed in a laboratory setting, all right? In the field, we're gonna make a note here, in the field, we can do this by drilling a pumping well, all right? Now, pumping wells and the calculations and the theory behind that, it can get quite complicated, and, how you go about performing that analysis will depend on if you have a confined or unconfined aquifer. So that'll be, we'll save that for another discussion in another video, but this can be done in the field. You can also use an empirical relationship. So I'm gonna make a note here, empirical relation. And there are several different empirical relationships, but one in particular is that's still widely used today is by Hazen from 1911. And he did this for clean sands, okay? Clean sands, usually of fairly uniform gradation. And what Hazen came up with empirically is that the hydraulic conductivity in centimeters per second for these kinds of sands is equal to a value called little c times the effective grain size squared, okay? So little c is an empirical, I'm gonna say constant ranging from about 0.4 to 1.2, and then D10 is your effective grain size in millimeters, okay? So what we see more often is the determination of hydraulic conductivity in the lab setting using a falling or constant head perm test. We also sometimes see it in the field by drilling a pumping well in an aquifer of some sort. But again, you have kind of the quick and dirty way of determining hydraulic conductivity using Hazen's empirical relationship. And again, it's valid for clean sands of mostly uniform gradation. And again, you're going to come out with units of centimeters per second for K, and then your D10 has to come from your grain size distribution of the sand, and that's going to be a value in millimeters. And again, it's D10 squared there, okay? So we're going to have some other videos that explore all of these different ways of determining K, but this is just them kind of summarized for us for the sake of this video. Hopefully you found this helpful. If so, please hit like and subscribe and be on the lookout for other videos like this. Thanks for watching.